So let's talk about QR factorizations. So one of the things we've been working on is developing these problems or phrasing these problems that we'd like to work on in the language of linear algebra. Now we want to sort of turn our attention to solving these problems more efficiently. So one of the methods for solving problems efficiently in numerical linear algebra is to construct what's called a QR factorization. So let's jump in and maybe do a bit of motivation. So at this stage, we've encountered two important operations. We've seen the operation of transposition, and we've seen the operation of inversion. Now, these two operations are different, but they have some things in common. For one, both operations are order reversing. So what does it mean to be order reversing? Well, the idea is that if we multiply two matrices together and then transpose the result, this is the same thing as multiplying the transposes together, but we have to reverse the order of the product. The same is true for inversion. If we want to invert the product of two invertible matrices, we can accomplish this by inverting the two matrices individually, but we have to multiply them together in the opposite order. So this is one thing that both transposition and inversion have in common. And they also have the property of being involutions in common. If we transpose a matrix twice, we get back the original matrix. And if we invert an invertible matrix twice, we get back the original matrix. So even though these operations are different, they have these two properties in common. Also, it's important to note that both of these operations are useful. So we've been very focused on the problem of studying systems of the form AX equals B, where A is given to us as a matrix, B is given to us as a vector, and X represents an unknown in the system. Well, approximations can be obtained by studying the least squares version of the system. To construct the least squares version of the system, we multiply the system on the left by A transpose. On the left-hand side, we end up with A transpose A, which is also called the Gramian of A. Then we're multiplying by X hat, the least squares approximate solution to the system. And then on the right, because we multiplied on both sides by A transpose, we are working with A transpose times B instead of just B. So multiplying by A transpose on the left gives us the least squares approximate version of the original system. And multiplying on the left by the inverse gives us an exact solution. So if we're lucky enough to be working with a system where the coefficient matrix is invertible, we could multiply the system on the left by A inverse, which gives us the formula A inverse A times X equals A inverse times B. And this, of course, is desirable because A inverse times A is not just some new matrix, it's guaranteed to be the identity matrix. So this gives us the exact solution to the system, X equals A inverse times B. So both of these operations are similar in the sense that they're both order reversing involutions, and both are useful for studying systems of equations. Transposition is useful for studying approximations via least squares, and inverses are useful for studying exact solutions by multiplying by A inverse. Now, there's an issue here, because as we have noticed so far, one of these operations is much easier to work with than the other. Transposition is much easier to do than inversion. And here's an example to illustrate this. To transpose a matrix, all we do is swap the rows with the columns. So here we have a perfectly good 3 by 3 matrix. To transpose, we don't really need to do any work. We rip out the 3 rows and put them into the 3 columns of a new matrix. Inversion, on the other hand, is a little bit more difficult. To invert a matrix, what we typically do, or what we have advocated for in class, is we augment the original matrix with the appropriately sized identity matrix. Then we apply the Gauss-Jordan algorithm until the inverse pops out on the right-hand side of that augmentation. So here we just have the same exact matrix. I bothered to invert this matrix, and I got a result. But the point to make here is that this result is not obviously predictable given the inputs of the original matrix, whereas the transpose is obviously predictable. So it's much easier to transpose than it is to invert. So what are the lessons to learn from these observations? Well, one, life would be a lot easier if transposition were as useful as inversion, and inversion were as simple as transposition. And another way to state this, maybe more mathematically, is to note that when A transpose times A is the identity, so when the Gramian of our matrix is the identity, many of the difficult problems we've been working on suddenly become much easier to work with. So if we think about projection problems, whenever we construct a projection matrix, the projection is of the form matrix A times the inverse of the Gramian of that matrix multiplied by A transpose. Well, if we know that the Gramian is equal to the identity matrix, inside of the parentheses here we have the identity, and it doesn't take any effort to invert the identity because the inverse of the identity is equal to the identity. So the projection formula simplifies dramatically when we know that the Gramian is the inverse. So projection becomes P equals A times A transpose. So if we're lucky enough to be working with a matrix that has this special property, projection problems all of a sudden are much easier to solve. Also, least squares problems become easier. The least squares approximate version of a system is A transpose A times X hat equals A transpose times B. Well, if A transpose times A happens to be the identity, this equation gives us a direct formula for the least squares approximate solution. This just tells us that X hat equals A transpose times B. So again, if we're lucky enough to be working with a matrix whose Gramian is the identity matrix, we automatically know that the least squares approximate solution to any system is given by just A transpose multiplied by B. So let's just see this in a simple example. So here we have a perfectly good 3 by 2 matrix A, and we have a vector in R3 B whose entries are 4, -1, -2. One thing to point out is that this matrix has the special property that we mentioned on the previous slide. The Gramian of this matrix happens to equal the 2 by 2 identity matrix. So convince yourself this is true by just multiplying A transpose by A and verifying yourself that you get the identity here. Well, what happens now is that projection becomes very easy. To construct the projection matrix onto the column space of this matrix, we know that we don't have to bother inverting the Gramian because the Gramian is already the identity. So projection onto the column space is just given by taking A and multiplying by A transpose on the right, and this one matrix multiplication gives us our projection matrix. So the projection matrix here is simply equal to A times A transpose. Also, if we wanted to study the least squares approximate version of AX equals B for this data, the system itself is A transpose A times X hat equals A transpose times B. But for this particular matrix, the Gramian is the identity. So we know that X hat is simply equal to A transpose multiplied by B. And if we do the matrix multiplication for this example, we end up with X hat equals 6 over root 2 comma -1. So here we just have an example illustrating how easy it is to do projections when the Gramian of our matrix equals the identity matrix. You can imagine how difficult problems are when you start from scratch, because if we didn't happen to know that the Gramian of this matrix equaled the identity, we might set up the Gramian and try to invert it, and that would impose a lot of extra steps here. So that's our new goal. Instead of working with ordinary matrices whose Gramian is not equal to the identity, our new goal is to work with matrices Q that satisfy the equation Q transpose Q equals the identity, rather than matrices A that don't satisfy that equation. Okay, so now I want to switch to think about maybe the geometry of this story. So far, the motivations we've given are completely algebraic. I want to now look at the geometric aspect of working with the equation Gramian equals the identity. So remember our visual representation of R3, where we have our three-dimensional axes, and each axis is spanned by one of the three standard basis vectors. So here we have E1, E2, E3, and these represent the three columns of the 3 by 3 identity matrix. E1 is the vector 1, 0, 0, E2 is the vector 0, 1, 0, and E3 is the vector 0, 0, 1. Well, one thing to point out here is that each one of these three vectors is a unit vector. The length of E1, which is 1, 0, 0, is simply equal to the square root of 1 squared plus 0 squared plus 0 squared. The length of E2 is the square root of 0 squared plus 1 squared plus 0 squared, so the length of E2 is 1. And the length of E3 is the square root of 0 squared plus 0 squared plus 1 squared, which is also equal to 1. So one of the things that makes the standard basis so special is that each one of these vectors is a unit vector. Another thing that makes this collection so useful is that they're mutually orthogonal. What does this mean? Well, what this is saying is that if we take any two of these three vectors and take their dot product, we always get the number 0. So if I take 1, 0, 0 and dot with 0, 1, 0, the result is equal to 0. If I take 1, 0, 0 and dot with 0, 0, 1, the result is equal to 0. And if I take 0, 1, 0 and dot with 0, 0, 1, the result is also equal to 0. So one of the things that makes the standard basis of R3 so desirable to work with is not necessarily that the numbers inside of these vectors are very simple. It's the more general fact that each one is a unit vector, and any two of these vectors are orthogonal. Now I want us to imagine that we do something geometrically relevant. So one of the things that we typically do when we manipulate pictures is we rotate them. So imagine that we started with our standard basis for R3, representing our three coordinate axes in three-dimensional space. And then just imagine that we rotated the axes. Well, after we rotate the axes, our vectors are definitely going to change. So in this figure, the figure is sort of constructed in such a way that after rotating, the original vector E1, which is the first column of the 3x3 identity matrix, becomes this new vector called Q1. And after rotation, this vector E2 becomes this new vector Q2. And after rotation, this vector E3 becomes this new vector Q3. So after rotation, E1, E2, E3 become Q1, Q2, Q3. So you can imagine doing some crazy rotation like this, and each of the vectors that we start with, which we think of as very nice, become vectors that are different in the sense that they have different coordinates. Another thing we might want to do when we manipulate axes is we might want to reflect them. So imagine we started again with our standard basis vectors representing our three coordinate axes for XYZ space, and then we reflect about certain coordinate planes. So here, this figure represents a situation where we reflect maybe the z-axis upon itself. So maybe the original positive z-axis becomes the new negative z-axis. And then in this figure, also maybe we're reflecting this blue vector, meaning that the original positive x-axis becomes the new negative x-axis. Also in this figure, it looks like maybe we're keeping the original y-axis the same. So we're reflecting through certain coordinate planes. Well, under this transformation, each of the three standard basis vectors become relabeled. E1 becomes this vector Q1, E2 becomes this vector Q2, and E3 becomes this vector Q3. So here we have two simple geometric situations, one where we rotate axes, another where we reflect axes. One thing to pay attention to in both of these examples is that even though we're changing the axes, we're not fundamentally changing the geometry. So the main way to communicate this is to say that rotation and reflection both preserve length. So when we rotate or reflect, we're not stretching the axes, which means that the original standard basis vectors, E1, E2, E3, when they become our new vectors, Q1, Q2, Q3, we get unit vectors. So the length of Q1 is 1, the length of Q2 is 1, and the length of Q3 is 1. So each one of Q1, Q2, Q3 is a unit vector. Also, when we rotate or reflect, we're not changing the angles between these vectors. So we haven't altered the angles between the standard basis when we reflect or rotate. So the new Q1, Q2, Q3 are also mutually orthogonal. If we took the dot product of Q1 and Q2, we would expect to get 0. If we take the dot product of Q1 with Q3, we expect to get 0. And if we take the dot product of Q2 with Q3, we would expect to get 0. So all of this is to say that after a rotation or a reflection, because the original E1, E2, E3 dot to 0 pairwise, each of the vectors Q1, Q2, Q3 dot to 0 pairwise. Okay, so let's use this geometric idea to define an important adjective that applies to a list of vectors. We say that a mutually orthogonal list of unit vectors is called orthonormal. So we check whether or not a list is orthonormal by verifying whether or not each vector in the list is a unit vector and verifying whether or not each pair of vectors in the list dot to 0. So here, as an example, we have two different matrices. This first matrix is a 2 by 2 matrix where every entry should be scaled by 1 over 13. We can check ourselves that the columns of this matrix form an orthonormal list. How do we do this? We check that the length of each column is equal to 1. So we would do this by taking 12 squared, adding it to -5 squared, and checking that that result is equal to the square, or is equal to 13 squared. Then we would add 5 squared to 12 squared, and checking that that result is equal to 13 squared. We would also check that these two columns are orthogonal to each other by taking the dot product of 12 negative 5 with 5 12 and verifying that we get 0. We can also check that the columns of this second matrix here are orthonormal by verifying that each one has length equal to 1, and also by verifying that each choice of two of these columns dot to 0. So a mutually orthogonal list of unit vectors is called orthonormal, and to verify whether or not a list of vectors is orthonormal therefore means that we check individually that each vector has length 1, and we check that a choice of any two of those vectors dots to 0. So the question now is, why are we talking about orthonormal vectors when we started this lecture by looking at the equation Q transpose Q equals the identity matrix? Well, let's make an observation here. Let's say that the columns of a matrix called Q, which here we're labeling as Q1, Q2 up to Qn, form an orthonormal list. Again, this adjective orthonormal means that each one of these columns is a unit vector and that any choice of two of these columns dots to 0. Let's now look at the Gramian of this matrix. If I transpose the matrix, the new rows are the original columns, so Q1, Q2 up to Qn are the rows of Q transpose. And then when I multiply by Q, I'm multiplying by the matrix whose columns are Q1, Q2 up to Qn. What is this product equal to? Well, if we take the row perspective on matrix multiplication, the first entry should be obtained by taking the first row of this matrix on the left, so Q1, and dotting with the first column of the matrix on the right, Q1. The 1, 2 entry would then be equal to the first row of this matrix on the left, Q1, dotted with the second column of this matrix on the right, Q2, and we repeat this process until we take all n squared of these dot products. So again, the 1, 1 entry is Q1 dotted with Q1, the 1, 2 entry is Q1 dotted with Q2. To obtain the 2, 1 entry, we would take Q2 and dot with Q1. To obtain the 2, 2 entry, we would take Q2 and dot with Q2, and so on. And now remember, the assumption we're making about this matrix we're working with is that the columns form an orthonormal list. Well, orthonormal means two things. Each one of the columns must be a unit vector, meaning that they dot with themselves to equal 1, and also each pair of columns here must dot to 0. So if we think about what this upper left-hand corner should be equal to, it's equal to Q1 dotted with itself, which is the length squared of this vector, which happens to equal 1. If we think about this entry here, we're taking Q1 and dotting with Q2. Well, orthonormal means that this pair of vectors, Q1 and Q2, must dot to 0. So once we start looking at each individual dot product in this formula, we realize that everything not on the diagonal here is a dot product of two different columns of the original matrix. And then when we look at every diagonal entry, we realize that we're taking the dot products of the repeated columns. And if we take a moment and think about what we're doing here, what we're doing is we're constructing this square matrix where all of the non-diagonal entries are equal to 0 and all of the diagonal entries are equal to 1. And of course, that's the n by n identity matrix. So this is exactly the connection between the algebra of the equation Q transpose Q equals the identity matrix and the geometry of the idea of orthonormality. When a matrix has columns that are all unit vectors and all mutually orthogonal to each other, that's exactly when the matrix satisfies this equation Q transpose times Q equals the identity matrix. So that's our major theorem. A matrix satisfies the equation Q transpose times Q equals the identity matrix if and only if its columns form an orthonormal list. And since we talked about the equation Q transpose Q equals the identity matrix earlier, its consequences are very desirable. When a matrix has a Gramian that's the identity matrix, projection problems are very easy to solve. So if we know that a matrix has orthonormal columns, we automatically know that projection onto the column space is given by one matrix product, the matrix multiplied by its own transpose. Also, if we know that a matrix has orthonormal columns, then we know that its Gramian is the identity, and any least squares problem becomes much easier to solve. If we're studying a system of the form Qx equals b, then, as we said previously, the least squares approximate solution is immediately given by x hat equals Q transpose times b. So we don't have to do any row reductions, and we don't have to invert any matrices to solve least squares problems when the coefficient matrix for our system has orthonormal columns. So here's an example to illustrate the power of orthonormality. Here we have a matrix Q, which is 3 by 2, and each of these two columns listed here should be scaled by 1/3. So the 1, 1 entry of this matrix is not -2, it's -2 divided by 3. We also have a vector here with 3 entries, 5, 2, -5. So you can verify yourself that the columns of this matrix are orthonormal, and one way to check this is to check the equation Q transpose Q equals the identity matrix for this example. Once we know this matrix has orthonormal columns, we can solve the least squares problem given this data. So if we're studying the system Qx equals b, we immediately know that the least squares approximate solution is given by x hat equals the transpose of Q, which is 1/3 times the transpose of this 3 by 2, multiplied by the vector b. And when we do the matrix multiplication in this example, we get x hat equals -3, 3. So we immediately solve the least squares problem because we know that the Gramian of our given matrix is equal to the identity matrix. Another thing we can do once we know this least squares approximate solution to the system is we can verify whether or not the system was consistent in the first place by just multiplying by Q. So remember that projection onto the column space of this matrix is easy to do once we know that its columns are orthonormal. Projecting B onto the column space is the same thing as multiplying by Q times Q transpose times B. And we just found that Q transpose times B is the vector -3, 3. When we multiply Q by the vector -3, 3, we get the vector 1, 4, -1, which is certainly not equal to the original B, 5, 2, -5. So here we quickly verify that the original B did not belong to the column space of the original Q. And we didn't have to do a single row reduction for the whole example. We only needed to do matrix multiplication, again, because we know that the Gramian of this given matrix is the identity.